Section 5.2 Trigonometric Equations. In this section we're going to be solving trigonometric equations which need use of the addition formulae which we studied in section 5.1. Example 5.2.1. Take a look at this equation and see if you recognize any patterns in this equation. Take a look at sine theta cos 15 plus cos theta sine 15. See if you notice any pattern there. I'd like you to have a think, pause the video and try and look back at the addition formulae and see if you can spot what we're going to do next. So pause the video, have a think. Well, here is a copy of what we get in the formula book. Here are the addition formulae. And I hope you noticed that what we have here fits the pattern of sine A cos B plus cos A sine B. So we're going to be making use of the sine addition formula. So the key in a question like this is to note that sine of A plus B, which we know is the same as sine A cos B plus cos A sine B, and that follows the pattern we have on the left hand side of this equation. So our equation becomes sine of something equals 0.4. Think about what the something is, look at the pattern we've noticed and try and write down what the something is before I do. Right, it's theta plus 15 degrees. We can check if that is correct by going back to the formula given to us in the formula book. Imagine we were given sine, open brackets, theta plus 15. How would we expand it? So it'd be sine theta cos 15 plus cos theta sine 15. Yep, that matches the question. So you've got to look out for these patterns and know when they fit the patterns of the addition formulae so we can use them. This has now reduced the difficulty of the question. Instead of having two different angles and also two different trig functions, sine and cos, we've now just got one trig function, which is sine. So we're going to do a little substitution. I'm going to let x equal theta plus 15 degrees, and now I'm going to solve sine of x equals 0.4 for x values between, pause the video and have a think, if theta is between 0 and 360, what would x be between? Right, well, x is 15 degrees more than theta, so x must go between 0 plus 15 and 360 plus 15. So we're going to find all the x values that satisfy this equation, and then at the very end take 15 off them all, and that will give us our theta values. I'm going to do a very quick sketch of the sine graph. There we go, quick sketch of the sine graph. I've gone slightly beyond 360 degrees because I might need to consider an angle all the way up to 375 degrees here. On the calculator, I did inverse sine or arc sine, whichever notation you prefer, of 0.4, and that gave me 23.578, and then more decimal places after that. I'm going to make sure I don't round that number. Before I pressed the inverse sine button on my calculator, I double checked that the calculator was in degrees mode. The fact that we want answers between 0 and 360 degrees tells us we're working in degrees here. So now that I've got that value from the calculator, I can now figure out if there's any others in the interval for this question. So the calculator just gave me 23.5 and so on. So then we're also going to have 180 minus that as well. And then is this one after 360, is that in our interval? Well, that's going to be 360 plus 23.5, which will be 383.5, and that one's too big. That one's too big. So it's just these two here that we want. So there are my two x values, and theta is what I want ultimately. So take away 15 degrees from x, and that will leave me with theta. Now this number 23.578, I'm going to store that in my calculator's memory. You can choose any letter you like. I'm going to store it under x on this Casio ClassWiz calculator that unfortunately you can't see. And then my first answer is going to be the number I've stored on my calculator, take away 15. And then the other one, 180 minus the number stored on the calculator minus 15. When the question doesn't specify how much accuracy to give, the general rule is 3 significant figures. So there we go, 8.58 degrees and 141 degrees, both rounded to 3 significant figures. Example 5.2.2. Take a look at this equation and note that we've got 2 pi in the range, and we've got pi over 3 in the question as well. These are signals that we are in radians for this question. Another signal is the lack of degree symbol anywhere. So we tend to assume radians from now on unless told otherwise. So get your calculator straight into radians mode, please. Once you've done that, take a look at the equation, and if you haven't already, pause the video and think, what could we possibly do in this situation? Well, I hope you've realized the only thing we can do is apply the addition formula. Sine open brackets a take away b, and kind of expand this bracket. That's all we can really do here. So we can do sine of a minus b, which is sine a cos b, take away cos a sine b. We're using the symbol at the bottom on the left hand side of the equation, so we're going to use the symbol on the bottom on the right hand side as well. So let's begin by expanding sine open brackets theta minus pi over 3. Pause the video and try and do that yourself. Right, I hope that's what you got. Sine theta cos pi over 3, take away cos theta sine pi over 3, and then don't do anything with the right hand side. Next, pause the video if you need to and think, how could we tidy this up or simplify it a little bit? I think the natural thing to do next is to turn cos pi over 3 and sine pi over 3 into number form. So cos pi over 3 is a half, and I've written it in front of the sine theta because it's neater and there's less chance of confusion. If you write sine theta and then a half afterwards, it's just a bit messy, and we're not sure whether the half is part of the angle or not. So it's easier to put the half in front. It's not only easier, it's just tidier as well. In the second term, sine of pi over 3 is root 3 over 2. Once again, I've written that in front of cos theta. Nothing has happened to the right hand side. Now, very important step coming up next. We've got 3 terms. 2 of them contain sine theta. 1 of them contains cos theta. Pause the video and think, what is our next move here? Right, well, if you haven't come up with any ideas, then I'll tell you what we're going to do, and then again you can pause the video and try and carry out that step. We're going to divide the whole equation by cos theta. That's what we're going to do. So pause the video and try and do that. Okay, I hope this is what you got. Half tan theta, take away root 3 over 2 equals tan theta. Now we were safe there to divide by cos theta. We can be confident cos theta is not 0 in this question, because if cos theta was 0, we wouldn't be able to divide by it, because dividing by 0 is impossible. Now how do I know cos theta isn't 0 in this question? Let's go back to this line here. If cos theta was 0, then theta could be 90 degrees, because cos of 90 degrees is 0. So this term would be 0. If theta is 90 degrees, sine of 90 degrees is 1. So we'd have a half times 1, take away 0, equals 1, which is not true. So that's how we can be sure that cos theta is definitely not 0 in this question, and we are therefore safe to divide by it. Right, you might be able to now complete this question by yourself. If you can, then pause the video and try and get to the end, and then check your answer against mine. If not, then the next step is to collect like terms. I'm going to take away a half theta from both sides of this equation, and then I'm going to double both sides. This is a point we always try and get to when solving a trig equation. You get a single trig function on its own with an invisible 1 in front of it. That's why I multiply both sides by 2 to get rid of the half. So we always try and get down to this point here, sine or cos or tan with an invisible 1 in front and then a number on the other side. So at this point I can do a quick sketch of the tan graph, and the question says 0 to 2 pi. Okay, there it is. It's a very rough sketch, but it will do the job. So tan theta equals negative root 3, which could be down here somewhere. So we're going to get that solution and that one as well. Remember, these solutions on the tan graph are always 180 degrees apart, or since we're working in radians here, they're going to be pi radians apart. Now if you do inverse tan or arctan, means the same thing, of minus root 3 on the calculator, you get negative pi over 3, which is slightly off my sketch I did. So if I extend it back here, this is the one the calculator has given me, which was minus pi over 3. And then working with the tan graph, like I said already, every solution is separated by pi radians. So to jump from one solution to the next on the tan graph, just add pi. It's easier to work with than the sine and the cos graphs. So my solutions in the interval for this question, 0 to 2 pi, are going to be, well, the calculator value plus pi, which will give me this one, and also the calculator value plus 2 pi, which will give me this one. So we've got minus pi over 3 plus 1 pi, minus pi over 3 plus 2 pi, which gives us 2/3 pi, and 5/3 pi as well. You can always check if those answers are correct by substituting them back into the original equation, making sure your calculator is in degrees. No, not degrees, radians of course. Make sure it's in radians, and if you get the same number on both sides of the equation, then you know these two angles are correct. Example 5.2.3. Solve 3 times the cosine of 2x, take away the cosine of 1x, plus 2 equals 0, answers between 0 and 360 degrees. As soon as you notice we're in degrees, make sure your calculator is in degrees mode. The first thing to notice here is we've got two different angles. We've got 2x and we've got 1x. We can't really go much further until we do something to this equation to make all the angles the same. They can either all be 2x or they can all be 1x. Here's the addition formulae, which on their own don't help us, but if you remember from section 5.1, we used them to derive the double angle formulae. Sine of 2x, cos of 2x, and tan of 2x. Because we've got cos of 2x here, we're going to need to think about which of the three versions for cos 2x do we need. This is a great opportunity, especially if you've only just learned the double angle formulae recently, to write down from memory all three versions of cos 2x. Pause the video and have a go at that right now. So we've got cos squared x, take away sine squared x. That's one of the three versions. We've also got 2 cos squared x, take away 1. And we've got 1 take away 2 sine squared x. In section 5.1 we learned where these come from and how to derive them, but you do need to memorize these for speed and fluency in the exam. So 3 cos 2x, take away cos x plus 2 equals 0. Have a think which of those three versions will be the best one to use right now. Okay, I hope you came to the conclusion 2 cos squared x take away 1. If you can't see why that's the one to use, then it's to do with what else is in the equation, and that's this cos x. We're not going to be changing that. We are going to be changing the cos 2x, but everything else is going to stay the same at the moment. So if we use 2 cos squared x take away 1, we're going to get an equation in cos x. If we chose one of the other two versions, we'd have an equation in cos x and sin x as well, which is more complicated. So choosing the middle version makes our job of solving the equation simpler. Okay, please make sure you put these brackets around. We've replaced cos 2x with two terms, so both of them need multiplying by the 3, so very important brackets here. Next I'm going to expand the brackets, collect like terms. You can probably see already we're going to have a quadratic equation in cos x. So please pause the video, expand the brackets, collect like terms, and if you can, get all the way to the end. If not, at least get it into the standard form for quadratic equations, where we have the squared term first, then the linear term, then the constant term, and it equals 0. So here we have it in standard form for quadratics. It equals 0, and we've got the squared term, then the linear term, then the constant term. I've also made sure when I've rearranged it, my squared term is positive. Again, that just makes my job easier. I'm going to try and factorize this now, but there are other ways you can solve it. You could go straight for the quadratic formula, or some calculators can solve quadratics for you. But I'm going to factorize this because it does factorize, and it's a very important skill to be able to factorize. So take every opportunity you can get to practice factorizing. That's what we get for this one. Mentally expand the brackets and check that you got what we had on the line above, or if you can't do it mentally, then write it down and check, because we can't afford factorizing errors. Now that we've factorized and it equals 0, that means one of the factors must be 0. If the first factor was 0, that would mean cos x is minus a third, because 3 multiplied by minus a third plus 1, that gives you 0. What if the second factor was 0? By the factor I mean this whole bracket. If that was 0, then cos x would equal a half. Both of these are going to give me solutions. So I'm going to sketch a graph of the cos graph and then get all the solutions between 0 and 360 degrees. So there's a very rough graph of the cos graph, or sketch rather, of the cos graph. And now we want to know, where does it equal a half? And where does it equal minus a third? So we're going to get 2 solutions for cos x equaling a half, and 2 solutions for cos x equaling minus a third. To the calculator, inverse cos of minus a third and inverse cos of a half. It'll give you 2 of those, then we've got to work out the others. So from the calculator, inverse cos, or arc cos, of minus 1/3, remembering that this question is in degrees. So once again, double check your calculator is in degrees. So we get we get 109.47. Not going to store that, sorry, I'm not going to round that number, I'm going to store it in the calculator's memory under A. And I'm also going to do inverse cos of a half, which is precisely 60 degrees. Let's go back to the graph. We can see this one is 60 degrees, and this one here is 109.47, and so on. So the next one that equals a half, using the symmetry of the graph, well, if from the maximum point to this solution is 60 degrees, then from the next maximum point to the left must also be 60 degrees from symmetry, because the graph is symmetrical. So it's going to be 360 minus 60, so that's going to be 300. And then the values for cos x equaling minus a third, well, we've got 109.47 so on here. And it's possible to get the other one just by doing, again, 360, take away that value. So from the beginning maximum point to there was 109.4 blah 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 degrees. Then from the next maximum point backwards, so to this one here, that'll be 360 minus. Well, this is 109.4 blah 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 degrees, so this bit here will be 360 minus that. Let's summarize our angles. We've got x is 60 degrees, we've got 109.47, so I'm going to round that to 109 degrees to 3 significant figures. And then our next one was 360 minus 109.4, which to 3 significant figures was 251 degrees, and then our final one was 300 degrees. Those middle two values have been rounded to 3 significant figures, but the first and last were exact, no rounding needed. And that concludes example 5.2.3 and also section 5.2. So now's a good time to practice solving trig equations where we need to use the addition formulae.